Welcome everyone to the 23rd meeting of New Directions in Group Theory and Triangulated Categories. Today, our speaker is Amnon Neeman from the Australian National University in Canberra, and he will be talking about finite approximations as a tool for studying triangulated categories. So yeah, please go ahead, Amnon.
אני אגיד לך שאמנון נאמן יש מבטא הודי.
לא, זה לא אמנון.
אני יודעת, הבנתי.
Thank you very much. So let me begin with very old stuff. So a metric, this was on a category defined by Lawvere, assigns a length to every morphism. And so this means a positive number. And identities have length 0. And if two morphisms are composable, then the length of the composite is less than or equal to the sum of the lengths. The triangle inequality holds. Now, we really only want to consider metrics up to equivalence. So if you're given two metrics on a category, then of course the category can be viewed as two categories with metrics, and the identity is a functor, and you can require it to be uniformly continuous in both directions. And if it is, you call the matrix equivalent, and you can give an epsilon delta definition, which is easy enough, I will leave up to you. The next notion, which is also very old, is Cauchy sequences. So a sequence of composable morphisms is declared to be Cauchy if the morphisms eventually become very short. And I should note that this depends only on the equivalence class of the metric. Two equivalent metrics yield the same class of Cauchy sequences. Okay, so now we'd like to complete a category with respect to a metric. And again, this is very old. So the basic idea is that you embed the category via your nada, and after embedding via your nada, you have embedded C into a category of functors which already has colimits. So you will simply form the colimits there. And to make our life, well, because our categories will all be additive, I'll assume C to be an additive category, a zilinear category, a category enriched over abelian groups. So this isn't essential, but nevertheless, it means that the Yoneda maps into the additive functors from C up to abelian groups. And as I said, for us, the completion will be just the set of all colimits in mod C of Cauchy sequences in C. And there is, I mean, for the experts, I note that there is a technical point here. You would like the completion of a metric space to be a complete metric space. And with this definition, L of C has a metric, but it's not complete with respect to the metric, at least not in general. But we will soon, okay. So the old literature deals with this, but we will soon assume our metric to be very special. So for us, this plays no role. So for us, L of C is as defined on the slide, and it is, as it happens, a complete metric space, a complete metric category. And so far, everything I've said is very old. It goes back to no later than the early 1980s. And now comes the first new idea. So we don't want to look at L of C, we want to look at the full subcategory S of C. And the subcategory S of C contains those functors which take sufficiently short morphisms to isomorphisms. So morphisms of length less than epsilon go to isomorphisms. Now, everything is so far, well, okay, with this twist, everything is old. And I only note about this that equivalent metrics lead to the same L of C and S of C. So these constructions depend only on the equivalence class of the metric. Now, we want to specialize it to a situation where we can prove something. So we will look at special metrics. So first of all, we restrict to triangulated categories. And the reason triangulated categories are better is because in triangulated categories, you have an idea of homotopy Cartesian squares, which allow you to translate morphisms. So given a homotopy Cartesian square, you consider any two parallel morphisms to be translations of each other. And a translation invariant metric is a metric which takes parallel morphisms to morphisms of equal length. Now, any morphism can be translated to a morphism starting at 0. And so to give a translation invariant metric, it suffices to specify the lengths of all morphisms starting at 0. So in other words, it suffices to specify the balls centered at the origin. Now, as I said, we will look at special metrics, and our metrics will in particular all be non-Archimedean. So up to replacing by equivalence, by an equivalent metric, we can assume the metric takes discrete values. In fact, we can assume the values are powers of 2. So we will allow the values of our metric to be 0 and infinity. We allow infinity as a value. And the other values are all powers of 2, positive or negative. And to know everything about the metric, it suffices to specify the morphisms which start with the origin, whose length is 2 to the minus n. And once you specify this, then of course you have a formula for the length of any morphism, which is easy enough to work out. Okay, and now we come to the definition of a good metric. So a good metric on S should be a translation invariant metric. So in other words, it's determined by the balls of radius 2 to the minus n. And we want the metric to be non-Archimedean. I remind you, non-Archimedean means that the strong triangle inequality holds. The length of the composite is less than or equal to the maximum of the lengths. And this translates to a convexity for the ball. So if B and B dashed both lie in the ball of radius 2 to the minus n, and X is an extension, then X also belongs to the ball. Now, you also clearly, just because it's a metric, have to have that Bn plus 1 is contained in Bn. After all, Bn plus 1 has half the radius. But we want the stronger containment. We want not only Bn plus 1 to be contained, but also its right and left shift. So if this holds, we call our metric good. And just to show you that there are examples, if S has a T structure, you can let Bn be S less than or equal to minus n. And now we come to a theorem. I mean, I've given you a whole string of definitions. So let's begin by reminding ourselves of everything. So if S is any category with a metric, then you can look at the completion, L of S, and inside L of S, you can look at this full subcategory S of S. We define them. If S is triangulated, you can define the triangles in S, the distinguished triangles in S of S, to be the colimits in S of S of Cauchy sequences of distinguished triangles in S. And the theorem says that as long as the metric is good, then with this definition of distinguished triangles, the category S of S is triangulated. And this is a theorem, and I should point out that it's a surprising theorem, because we've all learned that triangulated categories don't reproduce. In order to, it's accepted wisdom handed down over the years that in order to produce new triangulated categories, you need enhancements. And I'm speaking to an audience in Bonn. There are experts on enhancements. If Stefan Schwede did some of the beautiful early work on what would now be called infinity category enhancements of topological categories, providing categories which have more than one enhancement and showing that the homotopy category of spectra has only one. And well, one continues to be the center of beautiful work applying the infinity categorical techniques to arithmetic algebraic geometry, with prismatic cohomology and condensed mathematics. And elsewhere in Europe, you have other work about uniqueness of enhancements. Canonacco and Stellari have done lovely work over the years. And there's the work by, but actually most relevant to this talk is there's an old paper by Muro, Schwede, and Strickland, which produces a category with no enhancement. And last year, there's a newer paper by Rizzardo and Vandenberg, which produces many more categories without enhancement. And these are remarkable constructions. We basically don't know how to construct categories unless we do it via enhancements. And here is a theorem which tells you, it gives you a recipe which makes no mention of enhancements. I start with a triangulated category. It has a metric, and whatever objections you might have to this theorem, I told you the recipe. It wasn't very complicated. I told you how to construct a new triangulated category out of S. So, of course, in order to convince you that this is interesting, I have to show you by example that it gives something non-trivial. After all, if S of S is always 0, or if S of S is always equal to S, you will not be very impressed. So now we come to examples. So I'll remind you of the categories that will come up in the talk, and let me not explain them. So just look at the categories in red. If you know what they are, good, they will come up as examples. If you don't, just ignore them, they're different, that's the point. And so there's this one, and the red categories here. And what's relevant to us is that the S construction changes the category. It takes the bounded derived category of finitely generated projective R modules to the bounded derived category of finitely presented R modules, and backwards. So there's a metric with respect to which the opposite category goes to the opposite category. And similarly, for the perfect complexes, going to the bounded derived category of coherent sheaves and back. So this is definitely a non-trivial construction. So now, what I'd like to convince you in the rest of the talk, so this was the first theorem, and what I'd like to convince you in the rest of the talk is that this should really be viewed as part of a very general theory. And the big theorem that somehow behind all of this is that the category D of R and D, the category of all R of the derived category of all cochain complexes of R modules, and the derived categories of sheaves of OX modules with quasi-coherent cohomology are both approximable triangulated categories. So I have to tell you what an approximable triangulated category is, and I'll try to do this quickly. So the definition is here, and it's technical. I'm flashing it on the screen, and the way we want to think of it in this talk is as some kind of analog of Fourier series. So Fourier series are about taking a function from the circle to the complex numbers and approximating it by trigonometric polynomials. So you take a measurable function here and approximate it by an element of, by a Laurent polynomial in the exponential function. So in order to, ignore the column on the left. In order to do Fourier series, you have to start with the exponential function. You have to have some procedure of passing from the exponential function to the trigonometric polynomials of low degree. So you need the exponential function, you need the low degree Laurent polynomials in exponentials, and finally you need to be able to say what it means for f to be well approximated by trigonometric polynomials, so you need a Banach norm. So now we want some sort of analog of this. So our category will be approximable if, and here's the definition, and for us, the compact generator G is going to be the replacement for the exponential function. The T structure is going to be the replacement for the norm, the Banach norm, the LP norm. And this funny symbol here is going to be our analog of the Laurent polynomials of low degree. So now let's go a little more slowly through this. So I remind you what a compact generator is. And remember, this is going to be our analog of the exponential function. So in a triangulated category, an object G is compact if Hom G blank commutes with coproducts, and it generates if every non-zero object X admits a non-zero map from some shift of G. So this is very classical. Now we want an analog of the LP norm. And as I told you, well, okay, so we already know what a metric is. We even already know what a translation invariant metric is. We've met those concepts before, but somehow a norm is special in that the ball of radius 1 determines all the other balls. So if you know the ball of radius 1, then you know all the balls just by scaling. And for us, the way we will do an analog will be a T structure. So I remind you, a T structure, well, okay, here's an example. The standard T structure on D of R is given by specifying two subcategories, the positive and the negative objects. The negative objects are the ones with only negative cohomology, and the positive objects are the ones with only positive cohomology. And in general, a T structure on a triangulated category is a pair of full subcategories, the positive and the negative halves. And they satisfy some properties, they satisfy some conditions. And for us, the really key condition is the one in purple. And we want to view this condition, the one I've underlined, as saying that the ball of radius a half is contained in the ball of radius 1. And we do this by unilateral declaration. We declare t less than or equal to 0 to be the ball of radius 1, and the ball of radius 2 to the n is going to be the minus nth shift of the ball of radius 1. So the condition that the balls decrease rapidly enough is automatic from this. And the other axioms of a T structure guarantee the convexity of the balls. So this is, in fact, a good metric, with the definition of a good metric as before. Okay, so this is the norm. And finally, and now that we've decided what our norm is, we come to the Laurent polynomials of degree less than or equal to A. So given an object G and a positive integer, we have to have some procedure which produces for us more objects. Now, if you stop to think about it, the way to get new objects out of old ones in a triangulated category, well, there are not very many ways. You can shift, you can take direct sums, you can take direct summands, or you can take extensions, and you can combine these operations. So this is much like starting with the exponential function, taking linear combinations with complex coefficients of small powers of it. So now, there are old constructions which I will not use, but at least not use much. So this one is due to, so the one in yellow here is due to Bondel and Vandenberg in a 2003 paper. So here you place a bound on the number of allowed extensions. There is a construction due to Alonso Jeremias and Souto, also in a 2003 paper. Here, the bound is on the allowed shifts. And the new construction, this is going to be our Laurent polynomials of degree less than or equal to A, places a bound both on the allowed suspensions and on the number of extensions. So I don't want to go into details. I'm going to view this as a black box, but this is going to be our analog of the Laurent polynomials of degree less than or equal to A. Okay, and now we're ready for the definition. So a triangulated category is approximable if there exists a compact generated G. I reminded you what this is. A T structure, T less than or equal to 0, T greater than or equal to 0, and an integer A satisfying a couple of conditions. Now, the first of these two, the second of these two conditions, the one in purple on this slide, is best explained by a picture. So let me show it in a picture. So suppose you have an object F, which is in the ball of radius 1 around the origin. So the arrow from 0 to F has length less than or equal to 1. Then the condition says that there is an object E, which is a trigonometric Laurent polynomial of degree less than or equal to A, with our definition. And and an arrow from E to F of length less than or equal to a half. So in the light of everything I've said, this is natural enough. It says that you can improve approximations. So this is the second condition. The first condition says that G per contains T less than or equal to minus A union T greater than or equal to A. So this means that there are no non-zero homomorphisms from G into either T less than or equal to minus A or T greater than or equal to A. And this isn't particularly natural from the perspective of the analog with Fourier series. It somehow, what it says is that the exponential function and the norm are assumed to be compatible in a suitable sense. So I'm not sure I have a good motivation for this condition. It turns out to be a very strong restriction. This restriction specifies the norm up to equivalence. There's a unique T structure up to equivalence satisfying this. So it's a very strong condition. And what can I say about it? The only things one can say in its defense is that the condition is satisfied in many examples of interest, and it turns out to be very useful. Okay, so I've given you the definition of approximability. Next come the examples. So the first theorem should say that there are approximable triangulated categories. So here are theorems that tell you that some categories are approximable, and for this talk, the second of these is going to be the most important. The first will come up a little bit. Okay, and now for the second theorem. I have to convince you that approximable triangulated categories are actually useful. Oh, okay, so before the next theorem, the proofs are in these papers. Now comes the time for applications. And before I launch into the first two, I have to remind you of an old definition. So G is called, if S is a triangulated category and G is an object, you call G a strong generator if there exists an integer L so that every object in S can be generated out of G using no more than L extensions. So this is with the black box construction of a few slides ago. And the category is called strongly generated or regular if there exists a strong generator. And now we're ready for the first theorem, which is really an application of the theory. And this theorem, let me only give the theorem for Noetherian and separated schemes. So for Noetherian and separated schemes, the theorem says that the category of perfect complexes is strongly generated if and only if X is regular and finite dimensional. And the bounded derived category of coherent sheaves is basically always strongly generated. So it's strongly generated under mild technical hypotheses. So these are theorems, and if I were going to do justice to these theorems, I would have to tell you why one cares about them and the history. So I would have to tell you who proved what and when. And my experience is that this would take the rest of the talk. So there's been a tremendous amount of work done on this. much of the work is about estimating the integer L. Remember, the strong generation says that there exists an integer L with where S is generated out of G in L steps, and you can wonder about the best L. And this leads to various dimensions, the Rukia dimension, the Orloff dimension. One can worry about estimating this. Anyway, since I don't want to spend the rest of the talk about this, I will only say that there is a rich literature dating back 2 decades, really, about this. So the first result was due to Bandel and Vandenberg in 2003. Then this was extended and developed by Rukia in a 2006 paper, and later in a 2008 paper. There was an explosion of interest, so many papers on the subject. And I will skip all of this. The only thing I want to say is that what was known before these 2 theorems on this page was all in equal characteristic. And what's new about these theorems in the generality they are stated is that they work in mixed characteristic. Anyway, both of the results are now published. So there's a paper by Yoki, which appeared in August of this year, and a paper of mine, which appeared in May of this year. And this is all I want to say about these theorems, and my apologies. I'm not doing justice to them. But I want to move on to other applications. Anyway, so the next applications are all in preprint form, although there are surveys, published surveys in the literature. The research papers are on the archive, they're all in preprint form. So the first thing I want to discuss the rest of the theory. So the first thing I want to talk about is the equivalence of T structures. So for us, T structures give norms. In particular, they give metrics. And we'd like to declare 2 T structures to be equivalent if they induce equivalent metrics. So remember, the definition of equivalent metrics was way back in the beginning of the talk. To say that 2 metrics are equivalent is to say that the identity functor is uniformly continuous in both directions. Now, here we're talking about norms, which are very special metrics where the ball of radius 1 determines everything. So for 2 norms to be equivalent, as we know from Banach space theory, it's the same as saying that the identity is a bounded linear map in both directions. The ball of radius 1 with respect to one metric is contained in the ball of radius r with respect to the other metric. So if you spell this out, what it says is the ball of radius 1 with respect to the second metric, so T2 less than or equal to 0, is contained in the ball of radius 2 to the a, so T1 less than or equal to a, and contains the ball of radius T to the minus 2, 2 to the minus a. So it contains T1 less than or equal to minus a. So the T structures are a finite distance apart. And what's interesting is that there's a large class of examples of equivalent metrics. So if T is a triangulated category with coproducts and G is any compact object, then Alonso, Jeremias, and Souto taught us in a 2003 paper how to construct a T structure generated by G. So I should say that there's a rich literature following this. There's an infinity category version due to Lurie. There are many theorems of this type, but for us, okay, so first of all, the construction is explicit, it's given by formula. So in terms of our black box construction, the t less than or equal to 0 is given by this black box expression, and t greater than or equal to 0 is what it has to be. It's the right orthogonal shifted. And the important thing for us is that if G and H are two compact generators for T, then the T structures they generate are equivalent with equivalence as in the definition of a few slides ago. So this means that if the category has a compact generator, then it has a preferred equivalence class of T structures. You can say that a T structure is in a preferred equivalence class if it's equivalent to a T structure generated by a compact object. And this is independent of which compact, generated by a compact generator. And this is independent of which compact generator you look at. So there is a preferred equivalence class. There's somehow a norm that's better than all others. I've already hinted at this. There is the best norm. Now, up to equivalence. Now, given any T structure, it's customary to define T minus, T plus, and TB. So T minus is all the objects which are contained in T less than or equal to n for some n. T plus is all the objects that are contained in T greater than or equal to minus n for some n. And TB is the intersection. And equivalent T structures yield identical T minus, T plus, and TB. So if there is a compact generator in T, a single compact generator, then there's a preferred equivalence class of T structures. And the corresponding T minus, T plus, and TB are intrinsic. They don't depend on anything. So from now on, we only consider these. Now, the next thing we want to do is we want to look at the closure of the compact objects. So T is a triangulated category with coproducts. It makes sense to look at the full subcategory of compact objects. That's an old thing. But remember, because T has a single compact generator, there's a preferred equivalence class of T structures. So there's a preferred norm up to equivalence. And with respect to this preferred norm, you can look at the closure of the compacts. That is the collection of all objects F for which there exist arbitrarily short morphisms from a compact E to F. And the bounded part of this is the intersection with TB. And these T minus sub C and TB sub C are intrinsic. They don't depend on anything. So we've defined all of this intrinsic structure. So if T is a triangulated category with coproducts and a single compact generator, then out of thin air, we pulled out subcategories T minus, T plus, and TB. Those have to be thick. And we've also pulled out the closure of the compacts, TC minus and TCB, which are also intrinsic. And it's a theorem that if T is approximable, these categories are also thick. And in this context, it's interesting to know that it can, if you compute them, then you get very classical categories. So with T equals D of R, you can compute all of this intrinsic structure. And with T equals D sub QC of X, you can also compute all of these. And they agree with very classical subcategories. Okay, so far I've introduced all of these intrinsic subcategories, and now we have to head for a theorem. So before stating the theorem, I should remind you of some functional analysis. So let S be the space of Lebesgue measurable real valued functions on R. Then you can consider the pairing, which takes two measurable functions to the integral, where we declare the integral to be infinite if it doesn't converge. So it gives you a pairing from S cross S to the reals union infinity. Now, what a function analyst would do is restrict this pairing. So if you assume that F is in LP and G is in LQ, and you choose P and Q wisely, for example, 1 over P plus 1 over Q equals 1, then the inner product of F and G is actually a real number, so the integral converges, and it gives two maps from LP to the dual of LQ and from LQ to the dual of LP. And one of the first theorems to learn in functional analysis is that these maps are actually isometries of Banach spaces. So there's also a category theoretical version of this. So let R be a commutative ring and assume that T is an R linear category. Then the pairing sending AB to HOM AB, well, it's not symmetric. So you have to keep track of which one is first. So it's a map from T up cross T to R mod. And it induces a map from T to the dual of T up and from T up to the dual of T. So far, this is the ordinary Onega map. But following the motivation, the example from functional analysis, there's nothing to stop us from restricting to subcategories of T. And if T is approximable, we've just learned that there are 6 intrinsic subcategories. So we can restrict the pairing to any pair of them. After all, we can pair LP with any LQ. And in principle, we have many pairings we could consider, but the theorem is going to be about 4 of them. And I want to give 2 of them names. So I want to denote by Y the map from the closure of the compacts to HOM from the opposite of the compacts to R mod. And by Y tilde, the map from TC minus up to HOM of TCB R mod. So this is just so that I can state the next theorem. And because I don't want to run over time, what I want to note about this theorem is, I will not go through this theorem in detail. I will go through it very quickly. What I really want to note about this theorem is the generality. So it's true in this gorgeous generality about approximable triangulated categories, and it tells you something about the pairing. It tells you that sometimes the map from one of these categories to the dual of another is fully faithful or full, and it tells you precisely what the image is, the essential image. So let me skip the details and move on to the example. So if X is a scheme proper of an Eutherian ring, then D, the derived category of sheaves on X with quasi-coherent cohomology satisfies the hypothesis of the theorem. And in particular, the functor Y composed with I, the pairing of the bounded derived category of coherent sheaves with the opposite of the perfect complexes, gives a map which is an equivalence of the bounded derived category of coherent sheaves with a category of finite homological functors. So let's specialize even more. Let's suppose that the ring R is the complex numbers. So now, I mean, whatever else you may object that everything that has come before is abstract algebra or category theory. Now we have really come down to earth. We are down to the world of schemes proper over the complex numbers, and I should remind you just how concrete it is. So what is a scheme proper over the complex numbers? So to begin with, it's a compact Hausdorff topological space. Next, it has a complex structure. So it comes as a complex analytic space. So if I said complex manifolds, you'd all be happy. A complex analytic space is the analog where you allow singularities and you even allow it to be non-reduced. So locally, X has an atlas where the open cards have embedding into the ball in Cn, where the image is the zero set of a finite number of holomorphic functions. And the transition function, the gluing functions, respect the ideal generated by the holomorphic functions. And to give such a thing an algebraic structure, in other words, to make it a scheme proper over C, is to give a chart where the open subsets are zero sets of polynomials in Cn, and the gluing maps are polynomial. Now, it's known that a complex analytic space, a compact complex analytic space, does not have to have an algebraic structure. But it's a theorem that if an algebraic structure exists, then it's very unique. So this is a theorem which in its original version is due to Serre in 1956. It was published in a paper called Algebraique Géométrie Analytique. And ever since then, it's been known as Serre's Geiger Theorem. So the theorem asserts that if I give you...
I think on the screen that you're sharing, I can just see, suppose X is a scheme proper over C. Maybe it's just me, but...
Yes. Yeah, I'm coming.
Okay.
At the moment, I'm just remind you what the scheme...
Okay, no problem. Sorry.
Yes. So a scheme proper over C is all of the things I said, but the important thing is that the analytic structure determines the algebraic structure in a very strong sense. So in the sense that if I give you two possible schemes, so two possible algebraic structures, which are biholomorphic to each other, then the biholomorphic map actually has to be a polynomial map. So it has to be polynomial with respect to your chosen polynomial structures. The holomorphic vector bundles on X must be algebraic. The holomorphic coherent sheaves on X are all algebraic, and any map of holomorphic coherent sheaves actually has to be algebraic. It's given by polynomials. So as I said, this is a theorem due to Serre. It's called Serre's Geiger Theorem. And the relevance is that I'm about to show you a proof which uses the representability theorem. So the proof of any theorem starts with some trivial reduction. The way we prove a theorem is by first translating it into a different language. In general, yes. So there's always the soft part of the proof. And the soft part of this proof, which translates it into a statement about derived categories, says the following: there's a map L from the bounded derived category of coherent sheaves on X to the analytic version. You just forget that these are coherent algebraic sheaves and remember the coherent analytic ones. So this functor always exists, and it suffices to show that L is an equivalence of categories. So by the way, this reduction is already essentially due to Serre. So you could object that Serre's paper was in 1956. Back then, derived categories didn't exist. But the passage from what Serre does to what I said is soft, even by the standards of soft mathematics. So we have to prove that L is an equivalence of categories. And the idea of the proof is to look at this pairing. So you take an algebraic perfect complex and a bounded complex of coherent analytic sheaves to the maps between them, and the maps have to be in the analytic category. So Hom in the analytic category from L of A to B. So this is a pairing. It gives a map from the coherent bounded complexes of coherent analytic sheaves to the dual of the perfect algebraic complexes. And because X is compact, the thing in orange in the middle of the page is a finite dimensional complex vector space. So the above delivers a map taking B to a finite homological functor. And remember, the finite homological functors, by our theorem, by our representability theorem, are precisely the image of Y composed with I. So in other words, the representability theorem buys you that there has to be a unique factorization. So there must be a functor R, which makes the triangle commute. And now, so you've constructed out of thin air, out of representability theorems, a functor which takes a bounded complex of coherent analytic sheaves to a bounded complex of coherent algebraic sheaves. And now all you have to do is show that R and L are inverse equivalences, and that turns out to be an exercise. So I'll have to ask you to believe this. So I should give credit where credit is due. So the beautiful idea at the center of this proof, the idea of using the representability theorem, is due to Jack Hall. It's in this paper, which you can find on the archive. I mean, Jack Hall, at the time he wrote this paper, didn't have representability theorems powerful enough to pass directly from the idea to a full proof. And somehow what I did was try to prove representability theorems that allowed this passage. Anyway, so his paper is concerned about using representability theorems that aren't powerful enough to still push the proof through. What I try to show you is that once you have a representability theorem powerful enough, then it really becomes triviality. Anyway, so finally, for the first theorem of the talk, so remember, if S is a triangulated category with a good metric, we started out with a theorem that told us how to build a new triangulated category, S of S. And the issue was, the issue was what are interesting examples? So now I am ready to state the examples in the generality that I want to. So the generality is that for any approximable category, the S construction takes TC to TBC. And under mild hypotheses, it also goes back. It takes TBC up to TC up. And in particular, it takes the boundary-derived category of finitely generated projectives to the boundary-derived category of finitely presented R modules and back, and takes the perfect complexes to bounded complexes of coherent sheaves and back. And I should also mention that because the theorem is so general, it applies to other contexts. So if T is the homotopy category of spectra, then T is approximable, and you can compute what all of these intrinsic categories are. In particular, you can compute TC and TBC, and the general theorem applies, and it tells you that S of TC is TBC, and S of TBC up is TC up. So the final thing I want to say is that the results I described today are in the union of 5 papers. The first one has appeared. It appeared in May this year. Now, this is a sequence of 5 papers which build on each other logically. So, of course, I couldn't submit the second paper until the first paper was published, and I won't be able to submit the second paper and the third paper until the second is published. So it'll take a long time for these papers to be published. Now, for an old man like me, this isn't an issue, right? You can see the white hair. I'm old enough. It's not, I can wait for my papers to be published. But paper number 3 has 2 young co-authors. And if one of them, so those co-authors are not old, and if one of them applies for a job at a university near you in the next few years, then please bear in mind that through no fault of their own, their papers are taking a very long time to publish. Thank you very much.
Yeah. Thank you. Thank you, Amnon, for the wonderful talk. Can we all unmute ourselves and give this paper a round of applause? Right, so if you have any questions for Amnon, you can either unmute yourself and ask the question, or you can write them in the chat.
So you had this category T minus, for example, you said was independent of the choice of generator. Can you describe T minus in a way that's obviously independent of the choice of generator?
No, I don't know such a description. So Okay, I haven't really tried, but I mean, I should say that, so one question that people have asked me is to what extent this generalizes from schemes to stacks. So for an algebraic stack, one rarely has a single compact generator. And this theory falls on its face completely. So the representability theorems are false in the generality they're stated. So it's so, and the fact that for schemes there has to be a single compact generator is a theorem. So I guess what I'm trying to say is that not only don't I know of a description that doesn't use the generator explicitly, I'm not sure there will exist one, because somehow the T minus is intrinsically caught up with the fact that there exists a compact generator.
Okay.
Okay, it doesn't answer the question. I don't know.
Okay.
But,
Thank you, Neil. Any more questions for the speaker? In the meantime, let me take the opportunity to commend Amnon once again for going through so much detail and so many results. Yeah, sorry, please go ahead.
Yeah, at some point you had a functor, you had a y, a curly y, and you went through an analogy with the analytic situation, and in the analytic situation you had an isometry.
yes. So let's go back to this.
Sorry. Yes.
Yeah. So so in the analytic situation, as in the algebraic situation, in general, you'd expect LP to map to hum from LQ to R union infinity. So by restricting to LQ, the image is actually in the R dual of LQ. So in other words, the functor value lands in R. So this is similar to what happens in the algebraic situation. You don't expect to get all of hum. You somehow, the image will be those functors with certain special values. So in this case, because the image is representable, what you get on the right-hand side will have to be homological. And the next thing is it will, under the hypothesis, so there are hypotheses. The hypotheses are finite dimensionalities of the hum sets between compact objects. So under these hypotheses, the functor y takes its values in functors taking an object x to a finite R module. R is an Euclidean ring, so it makes sense for a module to be finite. And okay, so you don't expect the image to be the entire hum, It's going to be some part of the Hom, just as in the functional analysis situation. But if you're lucky, the functors, so 2 is the situation in which you're lucky, the functors will be fully faithful, and you will know exactly what the essential image is. So it's an isometry into its image. I mean, perhaps the thing to keep in mind is, back in the analogy here, is the case where P equals 1 and Q equals infinity. Because L1 maps to the dual of L infinity, but it's very far from the whole dual. It maps isometrically into a small part of the dual.
Mhm.
So somehow you want to describe the image. So you want to understand the image, and you want to know that you get an isometry. And that you have. So, okay, so of course it depends on making good choices. After all, you could study any pairing you want. But if you study your pairings intelligently, you will get a good theorem.
Okay, so the analog of the isometries is that you get a fully faithful.
Yes. And then you need to actually describe what the image of the isometry is.
Yeah.
Yes.
Okay, because you were talking about metrics before, so I was wondering if you can actually say something with with some metrics.
Good question. The first comment is that I haven't tried. I haven't thought about this. I don't know how to define a metric on the dual.
Right.
So the category on the right comes with a metric. I mean, it comes with a norm. We've been using it forever. I don't know how to define a metric on the dual category. No, okay, it's a good question. There might be a reasonable choice. Yes.
Yeah, thank you.
Yeah, thank you.
Thank you for the question.
There is a question about I want to be sure about one thing. Is it true that the homotopy category of spectra is approximable, since the sphere spectrum is
yes, so
compact generator, which is has no self-extensions?
yes, so let me, way back when, if you look at this.
This one, the first one, yes. Is I asked if the category of spectra does satisfy this condition one.
Yes.
Okay.
So if you let G be the sphere to be S0, then it satisfies this condition. There's no map from G into positive suspensions of G.
Yeah. Thank you.
By the way, D of R is approximable for the same reason. R has no extensions. There are no maps from R to positive suspensions of R.
Mm-hmm.
So those are somehow the easy examples of approximable triangulated categories. So as I said, the second fact, the fact that the quasi-compact separated scheme is approximable, is actually a theorem. It's not even an easy theorem. I mean, even the fact that there's a single compact generator is not, it is a theorem of Bundle and Vandenberg. And the compact generator is not explicit. It's an existence theorem, which isn't particularly constructive. So,
yeah.
So,
Thank you.
thank you.
Yeah, thank you for the question, George. Any more questions for the speaker? In the chat, no. Okay, I don't see. Okay. It looks like we don't have any more questions coming in from the audience. So yeah, so let me take this opportunity to thank Amnon again for this wonderful talk. We did record the presentation, so the video will be uploaded to the YouTube channel for the seminar series. So yeah, let's give the speaker another round of applause, please. Okay, yeah, I'm gonna stop recording now.